Controlled-STM, a two-stage model to predict the user's perceived intensity for multi-point spatiotemporal modulation in ultrasonic media haptics. Hello everyone, my name is Zhouyang Shen. My supervisor is Associated Professor Diego Martinez Plasencia. I worked the paper together with Zach Morgan, Madhan Kumar Vasudevan, and Professor Marianna Obrist from University College London. The advancement of contactless interaction has facilitated the development of various technologies aimed at delivering effective haptic feedback. Among these, ultrasonic media haptics stand out for its extensive utilization, owing to its exceptional resolution and the capability to provide a multi-point haptic feedback. Ultrasonic media haptic creates sensation by concentrating the acoustic radiation wave from arrays of transducers. Each transducer propagates the sound wave to the same position at the same time to form a focal point. However, such focal point is not perceivable. Different modulation techniques are required. The first technique is amplitude modulation, or AM. It works by modulating the focal point pressure over time and form the shape through different point layout. The lateral modulation, or LM, creates haptic shape by approaching the shape trajectory with multiple segmentation of lateral oscillations. The spatiotemporal modulation, or STM, renders desired shape by using single or multiple focal points to travel on the shape trajectory with certain speed or frequency. Both LM and STM delivers maximum pressure at all time. In this study, we mainly focus on the spatiotemporal modulation and its advanced version, multi-point spatiotemporal modulation. Many studies have mapped the spatiotemporal modulation parameters directly to users' perceived intensity. This includes the study of the effect of combined intensity used in a stimuli, the effect of drawing frequency, and of the number of focal points on a user's perceived intensity. However, these studies pose a problem, as such relationships are not transferable between devices, and the actual device output rendered by different parameter setting is not controlled. These uncertainties impede designers from predicting the effect of tactile stimuli than craft, and also limited the HCI researchers' insight into how humans respond to multi-point spatiotemporal modulation. We address this limitation by constructing a two-stage model. The first stage input parameters including combined intensity, drawing frequency, number of focal points, and device temperature, the different physical properties of the focal point, for example, the peak pressure or forces. The second stage builds on optimal physical properties among all to predict users' perceived intensity. 5 key properties are considered in this paper. Firstly, the peak pressure of the focal point is assessed, representing the maximum pressure exerted at the focal point. Subsequently, by examining the minimal perceivable threshold at various drawing frequency, the peak pressure relative to the minimal perceivable threshold is determined, providing the insight into the pressure relative to the perceivable threshold. Additionally, the analysis encompasses the integration of a force of a 2.1 cm diameter plates, a metric that is derived from the existing literature. Moreover, the absolute force exerted across the area perceivable to the user is evaluated as well, offering an understanding of the overall perceivable focal point distribution. Finally, the force across the perceivable area relative to user's minimal perceivable threshold is assessed, encoding on how the force distribution relates to the individual sensitivity threshold. In order to derive all these physical properties, a physical measurement experiment was conducted. In the physical measurement experiment, different device parameters were independently mapped to its corresponding physical effect. The combined intensity was mapped to the nonlinear effect, which illustrating the relationship between the pressure measured at each of the different combined intensity cases. The drawing frequency was mapped to the driving frequency effect, which demonstrate the relationship between the pressure measured at each of the different drawing frequency cases and drawing frequency that has been used. Subsequently, the number of focal point conditions were mapped to the power limit effect, which illustrating the pressure that has been measured at each different number of focal point cases under different commanding intensity conditions. And finally, the device temperature was mapped to the temperature effect, which is showing the pressure that has been measured at different temperature cases when doing the experiment. Subsequently, we mapped the derived physical properties of the device to users' perceived intensity through a user study, and find the optimal properties for later perceived intensity prediction. Finally, we obtained a complete model that is capable of accurately mapping different ultrasonic emitter haptic device parameters, including commanding intensity, drawing frequency, number of focal points, and device temperature to the optimal physical properties of the device and to users' perceived intensity. It's clear to see that the perceived intensity, which is showing as the orange line, is closely aligned with the physical properties derived from the device parameters. In conclusion, we observed that the user's perceived intensity is most correlated to the pressure above the minimal perceivable threshold. Our physical model can accurately predict the physical output of the device with an error of 7.8%. Our perception model can infer or inform users' perceived intensity introduced by the device with an error of 8%. Please refer to the paper for more details. Thank you.